Morning, everyone. So we're going to continue with our final review with Unit 3 today. Unit 3 is a section on solubility. So let's just work our way through here. Basically, this was an application to Equilibrium for solubility. For the solutions that we looked at, we were looking at dissolving a solute. You can imagine that it's a solid right now. You're dropping it. You can assume that the background is water. If something is soluble, it means it dissolves very well. Upon water, it becomes an aqueous state. Basically, if it's ionic compound, it basically rips apart. If it's something that's low soluble or insoluble, it's something that will end up as a solid. Later on, we refer to that as a precipitate. The type of equilibrium system that gets established here is for things that are both soluble and low soluble, you can reach a point where you basically maxed out the amount that can actually dissolve. That point is called the solubility. At that point here, we would have saturation where we have still a lot of ions that are dissolved. Usually those are homogeneous, so you actually can't see those particles, but there definitely is undissolved material present. So what is in equilibrium here is actually the dissolving reaction continues to occur, right? Solid is constantly jumping into solution, but macroscopically we don't see any changes because the ions in solution here are actually recrystallizing out at the same rate. Remember, concentrations are constant in time. The macroscopic characteristics don't change, but microscopically the reactions continue at the same rate. Forward rate equals reverse rate. So here's the first definition here. Solubility refers to this maximum amount. Every chemical would dissolve in water based on how much water that you have. It's the maximum that can dissolve in a given volume. For the given volume, we typically use per liter. Because equilibrium will depend on specific temperatures that we're at here, the solubility is also defined at a specific temperature. So let's say I have a cold cup of coffee, maybe the sugar would have crystallized out. If I heat up that cup of coffee again, the particles in the coffee start slipping and sliding past each other a little bit faster, and typically the solubility increases based on the increase in temperature. Sometimes they refer to solubility as the equilibrium concentration in a saturated solution. So let me just show you that bit here. Let's say I have an AB salt. An AB salt here, upon dissolving, let's say it becomes A plus and B minus. That could very well be A2 plus, B2 minus as well. At least here it's a 1-to-1 ratio. Solubility is always a number that describes a salt, and it describes here, very common, the units are grams per liter. So how many grams do you manage to dissolve before the saturation happens? Anytime you have grams and you want to convert it more so into moles per liter, so we can use mole ratio, we just need to do a mole conversion here. When we want to get rid of grams and go to moles, you see that we'll just need to use molar mass. So if they ever give you the solubility in gram per liter, to convert over to the molar solubility, basically solubility re-expressed in mole per liter, you just need to use molar mass as a comparison. Or maybe you've been doing a lot of work here with moles and mole ratios, things like that, and they suddenly ask you, well, how many grams? Again, just using molar mass of the chemical. If I manage to dissolve, let's say, this many moles in a given liter, this one here, depending on the mole ratio, the concentration of A plus in solution will be identical. It's the same number as how much has dissolved. In words, you can say, let's say I dissolved 5 moles per given liter. Therefore, the concentration would then be 5 molar, right? So you see, based on that 1-to-1 ratio, moles are nice because the mole ratio just works its way over. First part we did in this section here is just define, well, what are the chemicals that we're actually dissolving? Ionic compounds are specifically referred to as electrolytes. So if they give you a multiple choice question and they give you 4 choices, they say which one of these will form an electrically conducting solution, or which one is electrolyte. You're looking for an ionic compound. An ionic compound here will basically get separated by water. It's going to separate to form the positive and negative. Whenever we have charges in solution, charges that are mobile, it's the charges that can end up moving around, it's going to be conductive. It's actually more conductive the more ions that you end up getting. It's a non-electrolyte, or what's referred to as a molecular solution. If it's a covalent compound, you can bubble covalent compounds into water. Let's take CH4, so methane, right? Covalent, non-metal, non-metal. You can manage to dissolve methane underwater, right? We did methane bubbles before, but it turns out these bubbles here, because they're covalently bonded, they're going to stay as individual molecules. They don't end up breaking up to form charges, so therefore it's not electrically conductive. Right? So some of the terms that we did here, we pretty much, aside from this first starting bit here, well, you could try to dissolve covalent compounds. Those are non-conducting solutions. For the rest of this chapter, we focused here on electrically conducting electrolytes or ionic compounds. We use the terminology of saturation here. It's unsaturated when I'm sort of below this limit. There's no undissolved material, there's no equilibrium just yet. But saturation, that word actually already says to us there is an equilibrium, right? In grade 11, we had defined it. Well, as you start tossing it in here, saturation is the maximum amount this liquid here can dissolve. The instant that you see, okay, you added some solid and nothing dissolves anymore, that's saturation. In Chem 12, because we learned this concept of equilibrium, we're actually going to wait a little while here. Yes, you do want to have undissolved material present, but we're going to wait till an equilibrium is established. Wait till the forward rate actually equals the reverse rate. Still, saturation here does refer to the solubility maximum. So you've dissolved that maximum amount. Any extra material will be accumulated at the bottom. So here's the whole notion here. You can add extra solid to a saturated solution. Because you've maxed how much can dissolve in solution, none of this extra solid will actually be able to dissolve into the mixture. So you might very well have more solid or less solid because solids have a constant composition. We would still say the solids have the same concentration, and that's why we would ignore it in the KQ, KSP expression. What are the rates that are equal to each other here? Let's say the forward rate is the dissolving, so let's take the salt here and let's break it up. When these ions here are enough, when their trial value is actually big enough, they can actually start colliding good energy, good geometry, and recrystallizing to form AB, and that's called the recrystallizing rate. Forward rate equals reverse rate. So while a solution here may look homogeneous here, it looks like, oh, I just have powder left over on the bottom and there's nothing up top. That's actually a situation where you actually have the maximum dissolved in there. You can't just filter off all the solid and expect, oh, suddenly it's just pure water on top. In fact, there's still going to be a lot of dissolved ions. There is a notion of something referred to as supersaturation. This is when you actually play around with temperature. So when you heat things up, generally the solubility increases. So let's take a cup of coffee, let's heat it up to close to boiling, right? Let's dissolve all the sugar in there, let's make a saturated solution. I've hit this point forward rate because reverse rate, and now my coffee actually cools down. When it cools down to a lower temperature, less of that solute should be dissolved, and yet sometimes, because there's so much ion in solution and there's nothing really to sort of crystallize onto it, we can temporarily get maybe my coffee back at room temperature, where I actually have temporarily dissolved more than my excess amount. Usually what chemists would do here is if you just take a quick scrape with the side, right? If you basically build a little bit of a structure, then suddenly all the sugar will then crash out solution because it can just sort of build off of that crack or build off of that little scratch mark. So that's referred to as supersaturated here. We've dissolved more than enough based on a changing of temperature. Once you manage to help a few ions join together, the rest of it was going to crash out of solution fairly quickly. Making a saturated solution. So there's two ways of making the solution, which has solid forward rate equals the reverse rate here. The two main ways, the first way is let's take our solid and let's toss it into our container. Because we are starting off with our solid, this way here will definitely follow mole ratio. The other way of doing it here is we're going to have two solutions, one containing our first solution, I say our positive, one containing our negative solution here. You drop them in together. Sure, the unfortunate thing is because we're doing solution chemistry here, we need to do dilutions. We need to do a C1V1, C2V2 for the chemical on the left, a C1V1 and C2V2 for the chemical on the right. Once you dissolve those, suddenly your ions are in solution. Depending on whether they're high enough to hit your solubility limit, that's going to tell you whether they crystallize or not. In this case here, when you mix solutions, not mole ratio. You cannot follow the mole ratio here. So usually implied by the problem, oh, I dissolve a solid or mix solutions together. Usually it's pretty clear which way is which. Just be careful, again, for the mixed solutions. Just because you don't follow mole ratio, you also need to factor in this dilution bit here. When we're calculating, well, what's the solubility based on KSP? If it was totally up to me, well, let's think that it actually is dissolving a solid, so therefore I have more information. And we'll get to a problem like that. On our solubility chart here, we just arbitrarily defined a solubility limit. Something is low soluble if it dissolves less than this 0.1 molar. This one here is completely arbitrary, so 0.1 molar. So if you manage to dissolve any more than that, we call you soluble. Anything less than that, even at 0.09, practically you dissolve so little, again, given the temperature of 25 degrees, we can refer to as low soluble. In this section, you're going to see this phrase very commonly here: equal volumes of 0.2 molar solutions of A and B are mixed. Once you dilute them, because they were equal volumes, you're going to find that V1 and V2 is just going to be double what V1 was. So if you work out the math here, the concentration would actually drop to half. Half of 0.2 molar is actually 0.1 molar, and it basically matches up with the table. So you can look, does the table say low soluble or soluble? Usually we have two solubility tables that we look at. I try to look at the first one first. So this is the one that when we did net ionic equations and tried to find precipitates here, you checked it compound by compound. There's some that I would just memorize. So for example, if I have alkali ions, if I have H+, I have NH4+, with any negative ion, those ones here are soluble. Those ones here will always dissolve. Those ones will always be aqueous. Unless you really load it up really, really high, this one wouldn't be saturated. Going the other way here, if I have a nitrate with any positive ion also given as fully soluble. Remember on our table here, we gradually work from things that are most soluble. We get less and less soluble as I go downwards. And then we saw a method of sort of, it was called separating mixtures by precipitation, selective precipitation. We just basically try to do mix and matches to try to pull out one ion at a time. You do need to worry about charges. So for example, the fifth row down here, we're talking about the chloride, bromide, iodide here. Notice it starts separating. Well, chloride with many things is actually soluble, but then it says here, well, if it was with silver, if it's with lead 2+, if it's copper +1 ion, this charge here matters. So copper +1 and chloride, that one there was low soluble. But what about CuCl2? CuCl2 is actually copper using its +2 charge, and when it ends up using its +2 charge, that one there is actually soluble. Cu +2 would actually be under the soluble case. So do watch out for the charge as well. We can separate them by precipitation method. You'll always have your table with you, so you don't necessarily need to memorize, but there are some that are just helpful as hints. We talked about, especially for a double placement reaction here, we've been so far doing formula equations, basically using the chemical formulas, the chemical symbols to write all the equation. We can write what's referred to as a complete ionic or total ionic equation. Basically, you take anything that you've labeled as aqueous, anything labeled as soluble, and you break them up into their ions. You dissociate them. So dissociate, even though you might label something like, oh, I have sodium carbonate Na2CO3. Oh, but this one here is aqueous because this one here is an alkali salt here. This means that the sodium is actually no longer holding hands with carbonate. Water has actually separated the sodium ions from the carbonate ions. So when we do our complete ionic equation here, we'd end up writing that part there, 2 sodium and carbonate. Polyatomics themselves stick together here. Sometimes when you start writing the whole equation, you might end up with the same equation written, the same chemical written on both sides, and that's what's called the spectator ion, which you can cancel out in terms of a net ionic equation. For a properly worded question, your reactants should be in the aqueous state. We're putting them in aqueous, soluble, because then they can mix easier. When I have two products, it's totally possible that both of them are aqueous, then there's no net reaction, everything's a spectator. It might just look different. Maybe I do have one solid and one aqueous. That solid is referred to as a precipitate. We usually say PPT, just for short here. And that precipitate is a solid that crashes out of a solution. Previously, the ions were perfectly fine. You mix them together, there was an inherent dilution here, and they end up solidifying out as a precipitate. Then we started introducing some of the math we saw in chapter 2 here. For these saturated solutions, which mean we're at solubility equilibrium, we always put the solid on the reactant side. So even if you produced your precipitate out of this equation here, or precipitate was actually a product, we still put that solid on the left side. So let's take the solid here, let's say calcium carbonate. The reason why we prefer solid on the left side here, that way we have dissolving, as always, our forward reaction, calcium 2+ and carbonate -2. Because we are in equilibrium, we know we've waited long enough that the ions can actually recrystallize out, we've actually hit an equilibrium. Once you have that there, because this is an equilibrium, I can essentially define a KEQ. In this section, we had referred to it as a KSP. It is a solubility product constant. When I try to do a product over reactant ratio, you definitely include the ion concentrations, because those ones there are aqueous. Because the solid here is on the left side, we would end up dividing by 1, and we would always end up absorbing that into KSP. In fact, the bigger the KSP value, right, the higher the constant, That means you have to have more ions. More ions have to mean that your solid is actually more soluble. So there is this correlation that if you have a bigger KSP, it means it's more soluble. It means you have more ions in solution. Then we played around with that a little bit here. We did what's referred to as a tri-ion product. Specifically, when you did a mixing of solutions here, let's say calcium came to me in a solution of calcium nitrate. I would have, I don't know, make up some numbers here, 1 molar, 50 milliliters. I'm going to mix that in together with another solution. My carbonate actually comes from sodium carbonate. This one here, let's make it 1.5 molar at, I don't know, 25 milliliters. First thing I just wanted to allude to in this question is because we're mixing 50 and 25, your total volume is going to be 75. So regardless of whether it's precipitous or not, you have to end up doing a dilution. Well, what does this first dilution become? If I do a C1, V1 equals to a C2, the V2 is going to be 75 in both cases here. The concentration would have dropped. Similarly for the other side here, C1, V1, 1.5 times 25 equals to the new concentration times it by 75. Right? The total concentration would actually have dropped. Now, I am focused just on the calcium ions and the carbonate ions. We're never going to have a pure solution of just a beaker of just calcium ions, right? Having a charged particle is unstable. There's always some counterbalancing ion. No trouble though. These ones here, nitrates, we said were fully soluble. When this breaks up, we get calcium ions and we get 2 nitrate ions. Pretty much what you tell me about the concentration of calcium nitrate is going to tell me about the calcium ions, and in a similar fashion, you can figure out carbonate. At this point here, when I have my ions, I've done my dilutions here, it's possible that when you try your trial KSP, so trial KSP here, sometimes you call it a TIP, trial ion product here, it equally well would be calcium times carbonate. It's possible that after the dilution, maybe the concentrations are actually so low that your trial value is actually less. So let's give a number here. Let's say it's actually less than what it should be at KSP. KSP is what you need for an equilibrium. Well, what would happen here is if I find out my ion concentrations are too low, my Q is going to try to get bigger and bigger to end up getting KSP. For my Q value to actually get bigger, we need to have more ions. So let's do this here. When Q is less than KSP, more solid dissolves to produce ions. So this Q value, also called TIP, so TIP can get larger towards KSP. So we're starting to use this KSP here as my test value. That's what it should be when in equilibrium. If my Q value isn't big enough, then any additional solid that I have, maybe I had tossed in a little bit more solid, well, it's going to naturally break up to form more ions to try to bring up this Q value. What if we had the opposite? What if by the time I did my dilutions here, I figured out very often, what if my Q value here is actually bigger than the KSP? It's larger than what it should be. So far, my product over reactant ratio here is actually bigger than what it should be. It's a little bit weird to think about concentration of reactant because that's going to be a solid in our case. But generally, if Q wants to come down so that I can get closer and closer to KSP, my product ion has to go down. The only way for me to lose ions is for it to solidify out. That's actually going to tell me, yes, a precipitate forms. So usually this question is worded, does a precipitate form? Are the ions big enough? Is the Q value larger than KSP? We need to at least be KSP for a precipitate form. If the ions aren't low enough, no precipitate forms. At this point, we had a few little sort of spin-off applications here. We definitely did titrations quite a lot in this course here. Pretty much here, titration, we're trying to find some unknown concentration. Here's our key word. We're going to titrate it to a situation of equivalence. We're going to titrate it until there's actually no excess available. We actually have a really good count of how much reactant there is. Usually the titrations in this section here, they are definitely solubility titrations. We're going to call them chloride titrations. Turns out chloride, in the presence of silver, ends up solidifying out. This one here is actually a whitish precipitate. You would already see white forming. What we're going to do is we're actually going to throw in some chromate as an indicator. Turns out silver with chromate ends up showing a nice red color. Now this right here is a little bit weird when we're talking about sort of which solid is more soluble or less soluble. We just said usually the smaller the KSP, usually the less soluble it is. But this time here, unfortunately, when you try to work with the mole ratio, if I did it for AgCl, right, for this equilibrium, because it's 1-to-1 ratio, and x and x and x, then the KSP is just x times x. What if I did it for my silver chromate? Eventually, when silver chromate actually solidifies out, precipitates out, it's actually in a 2-to-1 ratio. So if I want to dissolve, let's say, a y of this, I get 2y and I get a y. So therefore, the KSP is actually going to be 2y all squared times y, which ended up being 4y cubed. Right? So you see that they're not necessarily on a level playing field here. We did the derivation during the lesson, and we figured out whenever there's silver present in both chloride and chromate, silver chloride actually precipitates before silver chromate. So if I did a titration here, let's drop in a solution of silver nitrate. Again, you're not going to have a pure bottle of just silver plus, that's unstable. We drop it into a Erlenmeyer here. I want to count how much unknown chloride there is. That's the concentration I'm interested in. I throw in a little bit of chromate indicator, so CrO4. So the CrO4 is present. As you drop in your silver nitrate, it's going to produce silver ions. As long as silver still runs into chloride, that's going to end up forming a white precipitate. No red forms yet. We're looking for the equivalence point here when you drop in that silver to kill the very last chloride, and now when you drop in an extra drop of silver, it can't find any more chloride to solidify with, precipitate with, and therefore it actually precipitates out chromate. And that's when the red, when that color change occurs, that signals the endpoint. Endpoint is when the color change happens. We saw a little bit more with acid-base indicators, and that's when you would stop. Lastly, there's an application here. Because solubility and saturation here are equilibria, we can actually play around with how can I shift the equilibrium, playing around with some ion that's in common. So very commonly here, especially in the prairies, we have water being referred to as hard water. That's because it has these heavy mineral ions inside. It causes a whole bunch of problems. It doesn't makes the water taste good, forms deposits that tend to clog sinks, inhibits soap action. It doesn't let soap form suds as easily in caverns, things like that. So if I have a tunnel here, sometimes those salt ions that end up sort of water running off from the top here, it's actually going to create stalactites. Sometimes those water droplets would hit the bottom and they end up forming stalagmites, things like that. So those are all sort of natural phenomenon. Pretty much we're looking at this solid forming, calcium carbonate. Calcium carbonate here is very often referred to as limestone. This is actually what our chalk is made up of. So far, if I have heavy water, or hard water, I basically have the presence of a bunch of these calcium ions. What I want to do is I want to try to remove these calcium ions. If I want to remove calcium, do I want to increase solubility or decrease solubility? If I want, as a consequence, for the calcium ions to be less, I want the equilibrium to actually shift left. So solubility is talking about the solid. The solubility number always comes for the solid here. Solubility describes how well things dissolve. I actually want to decrease solubility to remove this water hardness. Right? And what you can do here is you can add an ion in common. I can add calcium nitrate. Well, where did the nitrate come from? Nitrate just guarantees me I'm soluble. This will break up to form calcium ions and 2 nitrate ions. I could care less about the nitrate. If I increase the calcium concentration here, Le Chatelier being in equilibrium is going to shift. It's going to shift to the left to try to solidify out that calcium carbonate. It's a little more interesting trying to increase the solubility. If I, for whatever reason, wanted to make more of the solid dissolve, maybe it's clogged up my pipes and I want it to dissolve and actually run off with the pipe stem, I want to increase the solubility. Does it work by adding calcium carbonate? And I'm going to remind you here, calcium carbonate is a solid. Problem here is solids, they don't change concentration. So I might have, let's say, here's my container, I have a bunch of calcium carbonate. Let's say the concentration of solid. The concentration of solid would be, well, I have 3 particles worth in 1 box of solution, so 3. You can add in more solid. Inevitably here, yes, you can see more solid present. Okay, now I actually have 9 particles. Well, that would change concentration, right? But here, 9 particles, I'm divided by 3 times the amount of space. You'll notice that your ratio still is 3. So adding calcium carbonate, there's actually no shift because solids don't change composition. They don't change their density. They don't change their concentration. Sorry, composition. Okay? That doesn't mean all solids don't work. I can end up adding a solid here. Let's look up our solubility chart. Let's find something else that calcium solidifies out with. So calcium is actually low soluble sulfate. What if I added sodium sulfate? Na2SO4. Again, where did the sodium come from? I only am caring about the sulfate, but I'm never going to have a bottle of just pure sulfate ions. This is going to break up to form 2 sodium ions, 2 Na pluses, and SO4 minus 2. I don't really care about sodium. It was a spectator here. When calcium is in the presence of sulfate, this actually solidifies out as calcium sulfate. As it pertains to the initial equilibrium, it will pull down the calcium concentration, therefore shifting the equilibrium right, and therefore dissolving more solid, increasing the solubility. Okay, so hopefully that's a nice review of some of the concepts that we learned in this chapter here. We'll pick up our review for acid bases in the next lesson. Thanks, guys.